Hello everyone, today I'm just going to do a very quick first analysis of the footage of the Falcon Heavy's center core crashing into the sea next to the drone ship, which SpaceX released yesterday as part of a short edited recap video on the Falcon Heavy and Starman test launch. It's going to be a relatively short analysis since we didn't learn anything groundbreakingly new from this footage. It mostly confirmed what we already assumed. We now know for sure that the booster ran out of ignition fluid, so that the two additional engines for the landing burn didn't ignite. It basically performs a suicide burn, igniting its engines at the last possible moment to slow down just in time and stop just over the landing pad or the drone ship and then drop down. But then in this newer, more fuel-saving version of the landing that they tried out with the center core of the Falcon Heavy landing and a few other cores before, that suicide burn is divided in 3 stages, which not only saves fuel but also helps increase precision and reliability if it actually works, although you do have to ignite engines 2 more times. In this version of the landing it ignites the center engine for the slowdown and landing burn, then a tiny little bit later it ignites 2 more engines around it to perform the bulk of the slowing down with 3 engines, thus more thrust, a faster deceleration, less gravity loss and a more efficient landing. It also gets more precise and soft, as just before the actual landing it shuts down these 2 additional engines, then uses the 1 remaining engine for the last part of the slowing down, and then stops that when it just comes to a halt just above the landing pad and drops down. Now you have to keep in mind that while the Merlin is relatively versatile and can be throttled relatively well compared to some other rocket engines, it still can throttle down further than to 60% throttle. And while ignition takes a little while, the shutting down of rocket engines is a relatively fast and precise process. So even though tiny corrections can be made with throttle, that last shutting down of 2 engines essentially provides an additional point at which a correction can be done. By timing the shutdown of these 2 engines, a last correction can be done to that landing burn, increasing the precision of the landing. Now what happened during the center core landing of the Falcon Heavy launch is that while the rocket still had enough fuel left and a tiny reserve, although that is pretty small, it ran out of igniter fuel, not the actual rocket fuel that the engine runs on, but the igniter fuel that is burned in the ignition system that is used to turn the engine on in the first place, and so the 2 additional engines didn't actually ignite, since the landing was planned for 2 additional engines and the first engine was ignited with the additional 2 engines basically in mind, or rather in code, as the Falcon 9 of course lands by autopilot. The rocket with a thrust of just 1 engine simply couldn't slow down enough to do a soft landing, instead crashing into the sea at a high speed. The exact reason for this is still to be further analyzed. Now it seems unlikely that it just didn't have enough ignition fuel on board. It's possible, since that technique is relatively new, but it has been tested a few times before and it failed on the Falcon Heavy, so it seems likely that there may be some further reason that is actually related to this core's flight. And being boosted by the additional booster cores of the Falcon Heavy, this core had a relatively long coast phase in space compared to other Falcon 9 first stages, and a relatively hard re-entry, and between slosh and boil off and any number of other complicated reasons that might have contributed to the already almost depleted ignition fluid not being able to light the engines. Another thing you need to know to analyze the failed landing of this car is that that final landing burn does mainly 2 things. It slows down the rocket, but it also shifts the rocket to the side, because reliability and safety is in a way already planned into this. And so the landing procedure for the Falcon 9 first stages actually starts by aiming to the side of the landing pad or drone ship, and the landing burn then shifts the rocket to the side, does one last sideways flight onto the drone ship before slowing down, evening out and dropping onto the drone ship. which is done just in case for this or similar incidents where the landing burn fails to ignite, the engine fails during the landing burn, or anything else fails close to the landing and the board computer decides to abort that landing, that a crashing Falcon 9 does less damage to the landing pad or the drone ship by crashing next to it rather than crashing into it. Now this doesn't always work perfectly. A few very early test flights, despite this and despite failing to land, still hit the drone ship back when the suicide burn was simply misscheduled or something went wrong later on during that landing burn, but in this case it actually did make the rocket miss the drone ship. Now the footage adds a few more little details. We know now that the rocket, while it did miss the drone ship and did go way too fast, went slower than previously thought and crashed closer to the drone ship than previously thought. Now these are relatively small differences, so it's not really a huge change to what we knew, but it's still interesting, and while further analysis of the data and the footage is still coming, we can make a few additional speculations based on this. Now it's important to keep in mind that it always looks a lot slower and a lot closer than it actually is. It's a similar effect as with any large objects without proper context. Oversized vehicles, large airplanes and rockets basically have that psychological effect where you misestimate their size and anything related to it when you see them without any good comparison for their size. For example, we know that an average airliner is maybe 20 meters in wingspan, and so when we see a really large airplane like the Airbus A380, even if we know that it's a lot bigger, we still subconsciously assume that it's somewhat similar or only a little bit bigger in size than other airplanes, and thus compared to its size we then also misestimate its distance and speed. It looks really slow because it is really big, and relative to its size it's not moving as fast as other airliners because it's moving at the same speed, but it's bigger. And when seeing a Falcon 9 without anything to compare it to and without knowing how big it actually is, or even when we know how big it actually is, we kind of subconsciously assume that this thing is some 10 or 20 meters in size, while in fact the complete Falcon 9 is 70 meters high and the first stage with the interstage is some 50 meters high. And so it looks to be going a lot slower and being a lot closer than it actually is. However, that aside, when knowing how big it actually is and analyzing the footage we have and making a rough estimate as to how far away and how fast it was, we still get a lower estimate than what was previously assumed by SpaceX, which is interesting since while the landing still failed, it tells us that the landing burn was basically a little bit more successful than we previously thought. Keep in mind that tiny corrections can be done by throttle, and we see that during the crash the one engine that did ignite is running at full throttle. We also see that the rocket is heavily tilting over, essentially trying to get onto the drone ship, which means that perhaps the board computer didn't properly react. The landing legs never deployed, which may be because it reacted to the failure, or may just be because it never reached the velocity at which that is triggered. The landing legs only deploy at a certain speed, and it never actually slowed down to that speed. So it may be that the board computer was essentially still trying to land on the drone ship and just hopelessly failed, rather than as previously thought noticing that two engines failed to ignite and thus triggering an abort command that would change the autopilot's goal and try to crash the rocket as far away from the drone ship, doing as little damage as possible. Now we still don't know this for sure, and we also don't know why this might not have worked, but SpaceX is still doing further analysis into it. The difference isn't that big, and the rocket still crashed at roughly 120 meters per second, about 100 meters east of the drone ship or 150 meters east of its landing spot in the center of the drone ship. And while it did do some damage and put some debris onto the drone ship, at least this way we get a spectacular view of the crash within the field of view of the drone ship based camera. And given that no one was actually hurt in the crash, obviously, we now have another spectacular crash to enjoy in a SpaceX crash reel, and more information about the failure which might help to find the source of the problem, which is of course relatively easy to fix by just putting more igniter fuel in. So we can hope for a successful triple landing with the next Falcon Heavy launch, which is actually scheduled in June. If we learn anything more until then, I will keep you up to date. And as I find the time, I will also do more explanations about more theoretical background topics on physics and spaceflight. So if you have any spaceflight, aviation or physics related questions, I'm always open for requests, and as always, thanks for watching.